Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently working at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And yeah, I'm a theoretical physicist. Specifically, I study cosmology. So that means that I study the universe, the contents of the universe, cool stuff happening inside the universe, how it all fits together. It's a cool topic. I love being a cosmologist and I love chatting to people about all of the cool things I get to research. It's really, really fun. Great to see all of the regulars joining. Scott, Paul, Prof, David, great to see everybody. Welcome. Great to have you here. For anybody who's new here, welcome. Hope you enjoy it. This is an interactive stream. The idea here is that you can ask me anything you want about cosmology, about physics, about science, about life, about academia, basically anything you want. And I will do my best to try to answer. So feel free to jump in with any questions. Otherwise, if you don't have questions, I get to ramble about my favorite topics. Hey, Ange, great to see you as well. So yes, Cup of Cosmology has been absent the past 3 weeks. I have been up to way too many things. I've been traveling, went through a bunch of countries. I lost track of how many countries I've been through the last 2 or 3 weeks. A lot of it was by train, which was extremely fun, but it's been busy couple of weeks with a lot of like social events as well. I was at a wedding, I was at a christening, I got ill at both of those. I did a bunch of things, fell over, injured myself. It's been an eventful few weeks, but it does mean Cup of Cosmology has been on pause. But today we're back to regular schedule, but not really, because I'm back today and then I'm going to be gone again for the next at least 2, potentially 3 weekends, because I am once again traveling, this time for work. Also multiple trains involved. I think I have 2,400 kilometers left to do by train in the next 2 weeks. So it's in the next 3 weeks. So it's going to be a lot of busy stuff happening from my side. So Cup of Cosmology is back today, exceptionally, and then there will be a 2 or 3 week break again. But then come October, I should be back to regular schedule. So October, November, you can expect, and probably December, you can expect to stream every weekend with maybe 1 or 2 exceptions. So just bear with me these months while I'm busy doing way too many things for everybody. And then I'll be back to regular schedule soon. So, as I said, this is an interactive stream. So the idea here is that you can ask me anything you want about cosmology, about my research, about, life in general. I definitely don't have the answers to life, the universe, and everything, unless you want the answer 42. But otherwise, I can try to answer any questions you have. So as a reminder, I've worked on a lot of things. So there's a lot of things you can ask me about. If you want to ask me about some of my favorite topics, you can ask me things like, what is this amazing picture that I show every single stream? This is the cosmic microwave background radiation, one of my favorite things in the universe. You can also ask me about gravitational waves, which are also one of my favorite things in the universe, or dark matter, or the arrow of time was a fun one that came up recently. The Fermi paradox. These are all topics that people have talked about recently, so feel free to ask away. How plausible is news of possible early universe supermassive black dark matter stars, dark stars? So I haven't read the news. I haven't heard that news, but there could have been. So we have an idea of the history of the universe that started with radiation domination and then entered matter domination and then dark energy domination. So what do we mean by this? In the early universe, there was mostly radiation, photons, particles of light, and a lot of high energy particles just zipping about doing their own thing. We call this radiation domination because it is dominating the mass of the universe, or the energy of the universe, sorry. Now, as the universe expands and cools down, radiation dilutes away faster than other components. It kind of spreads out faster than matter does. So at some point, once radiation has spread out, we enter a period called matter domination. During matter domination, matter is the most abundant part of the universe. At this point, we're talking about both normal matter and dark matter. So just as a reminder, the universe has 3 main components. Everything you see, everything you're accustomed to, everything from me to my coffee mug to us, all of this is normal matter, 5% of the energy budget of the observable universe. 26% is in the form of dark matter, which is this weird type of matter that interacts via the gravitational force, but doesn't interact electromagnetically, so we can't see it. And dark energy makes up the remaining almost 70%, and it's this weird energy that is driving the accelerated expansion of the universe, and that's pretty much everything we know about it. So, early universe, radiation domination. Second phase, matter domination, because radiation dilutes away faster. In matter domination, dark matter is the dominant part of the universe. And then dark matter dilutes away faster than dark energy. So at later stages in the universe, we enter dark energy dominated stage. So these are the kind of the three, today we are still in the dark energy dominated stage. So these are the three phases, but there are hypothetical changes to this. For an example, there could have been a phase before radiation domination or in between, which would be like an early matter dominated phase where matter could have dominated for a while and then kind of annihilated, decayed, gone away for whatever reason, then radiation dominates again, and then we start the actual cycle that we know. This could happen, for an example, if you have primordial black holes. So primordial black holes are a type of black hole that is formed in the very early universe. So the black holes we're used to thinking about are the result of stars reaching the end of their lifetime, exploding and collapsing and leaving behind a massive, massive, massive remnant, which we call a black hole. Key distinguishing feature of a black hole is that nothing can escape, not even light. But you don't need to go through the whole star formation process. In the early universe, if you have fluctuations like vibrations of matter, not really vibrations, but differences in the density of matter, which we know we expect from quantum mechanics, from quantum physics, this could lead to primordial black holes forming regions of space-time that are so dense that they just collapse upon themselves and form these primordial black holes. Now, these primordial black holes could have constituted, or could have been massive enough and dominated enough that they could have triggered an early matter-dominated epoch before the radiation epoch. So then the three stages that I mentioned would have another one that was like an early matter domination phase. The reason I'm rambling about this is Paul's question: how plausible is news of possible early universe supermassive black holes or black stars, dark stars? So it depends what you mean as dark stars, but for an example, these primordial black holes could be constituted as dark stars in a way. They're basically a type of black hole. So this is a possibility. And there's other mechanisms by which you could just form clumps of dark matter in the early universe. But we do need these three cycles that we're aware of radiation domination, matter domination, and energy domination in this order in order to explain a lot of things we see in the universe. So if you add these like early matter dominated phase where you have these black holes in the early universe, then they have to be short-lived. They have to go away for some reason, because otherwise you'd mess up the time at which we change between radiation and matter. And this is something that we can actually measure quite accurately thanks to my famous friend, the CMB, the cosmic microwave background radiation. So by using this light here, you get it 2 times within the first 9 minutes today. By using the afterglow of the Big Bang, these leftover photons, we can get an idea of at what point we change between radiation and matter domination. So if you add this early period of matter domination beforehand, it has to go away, because otherwise you're going to mess up these later stages that we know of. So how plausible is it that we could have had dark stars? It's not impossible. It could actually fit in the history of the universe. It's just a problem that you need to then make this go away, at least make it not be dominating, so that then you can have everything else. Of course, what you could argue is that you want some dark stars in the early universe, but not enough of them to dominate the energy budget and to trigger this early matter-dominated epoch, but just enough to kind of be there. And that is plausible. That could happen. It's not ruled out. Doesn't mean it's likely. There's always the threshold there of what is likely, what is ruled out. How do we statistically quantify these things? But it is possible that in the early universe there were bigger clumps of dark matter. So we have limits and bounds today on how big dark matter can be based on things that we see. For example, if today dark matter was in the form of massive, massive, massive stars, you would get a lot of lensing. Because we don't have as much lensing as we'd expect with this case. This is why we say dark matter is probably not in big dark stars today. But that doesn't mean that dark matter wasn't in the form of stars that then, for whatever reason, decayed or unattached or became non-functional bodies. But there's also the fun thing that today we would call these objects machos, for example, massively compact halo objects. This is a hypothetical type of dark matter that, instead of being a particle like most of the dark matter we look for, would be a star. or a big clump, not a glowing star, but just like a big star-sized object of dark matter. Now, as I mentioned, if you have an object, a big object in the universe, any light coming behind the object, from behind this object, will be diverted due to gravitational lensing. So if you have a big star here, or a big galaxy, or a big clump of dark matter, or whatever, any light coming around is going to feel the curvature of space-time caused by this object, and is going to bend around it. Once the light reaches us, we trace it back and we get weird images. You might have all seen in the Hubble deep field images or the JWST deep field images, there's these galaxies that are kind of distorted and lensed. This is gravitational lensing, and this is what happens when you hold up a lens to the universe, or in our case, when you hold up a big massive object that distorts space-time and makes light go wonky. Based on the amount of gravitational lensing we've observed, we can say dark matter is probably not in big stars today. However, some people say that this is not a valid conclusion because it assumes that there's a specific assumptions that go into this that have been questioned. This is why today primordial black holes that are still alive today are a viable dark matter candidate. So we could have a population of primordial black holes or dark stars that were formed in the very early universe that could still be alive today, and they could make up the dark matter. But this is a highly controversial and contentious topic because depends how you do the analysis, depends what assumptions go into this. It's either possible or it's not. And I just want to be clear here because I've used the two interchangeably. Dark stars and primordial black holes are not necessarily the same thing. You could have a different type of star that has a different formation mechanism, star, but completely dark, like a dark matter star. These are not necessarily the same thing, but they have the same properties. So when I'm talking about primordial black holes and dark stars, I'm treating them as the same class as object, but they are not necessarily the same object. So that was a long-winded answer, but the short version is, yes, it is plausible that we could have dark stars in the early universe, but this is a scenario that we have a lot of constraints for. We can't rule it out, but it is constrained. Beyond the headlines, it turns out these theoretical stars are not made of dark matter. Dark stars made of hydrogen and helium, but powered by dark matter heating. Oh, well, that is cool. So how would that work? So most stars that we know of are made of hydrogen and helium. Hydrogen and helium, you put enough pressure there, you can start fusion, you fuse them together, hydrogen fuses heavier elements, and you've got yourself a star. Powered by dark matter heating. Now, how would that work? That is very curious. I'm going to have to read the article because right now that doesn't make a lot of sense to me because dark matter doesn't, to our knowledge, interact with hydrogen and helium, or at least not extensively. So any interactions there would have to be very small. And dark matter heating up the star. Yeah, I'll have to look into that. That's a very interesting idea. One that I've never encountered before, or at least that currently is not in my brain. So I will look into that. I'm going to make a note of that because that is very cool. Dark matter heating stars. Huh. Curious. This is the cool thing about dark matter. There are so many possibilities that really our imagination is the limit. Because you can just come up with a new model, a new random dark matter model. And, if the data allow it, then you say, well, it's as likely as all these hundreds of other dark matter models. Why not? I think the weirdest dark matter model that I've worked on, the weirdest from my idea, was this idea that you could have primordial black holes in the early universe. These evaporate via Hawking radiation, which is this process by which black holes lose a bit of their mass and kind of gradually evaporate or dissipate. And that the evaporation of these primordial black holes would produce the dark matter. So it's like dark matter produced by evaporating primordial black holes. And when I worked on this model, I was like, how? What? Why? But it's a really cool model. A lot of people work on it, and it's actually kind of makes sense. And it's a scenario we can't rule out. Well, we constrained it, but we can't rule it out. So that was a very fun thing to work on. So yeah, until we can actually figure out what dark matter is, you can play about with a lot of things. And the idea of dark matter star sounds really cool. I will have to look into that. If you had a normal star, but with say 25% of its mass as dark matter, would it burn hotter or colder than an all normal matter star? So assuming that dark matter is not doing anything in the star other than just being a clump there, then you basically have less mass in your star overall. Well, not less mass, but less usable mass that you can use for fusion. Assuming the dark matter is just there and not actually participating in the star itself, which might not be the case. But let's assume that the dark matter is just sat there not doing anything. Then you can only basically access 75% of the star for the energy fusion process, which means you have less energy available. So then it would fuse less, which means it would be colder and slightly bigger. Yes, that's the way that goes. Yes, there's a diagram that I can never remember that relates the mass of a star and its temperature and its luminosity, how bright it is. It's called the Hertzsprung-Russell diagram. And I can visualize it, but I can't remember what goes where. So yes, if it only has 75% of its mass to burn, assuming dark matter is not in any way involved in this process, then it would be less energetic, less hot, colder. Yes, fun questions. I like these fun questions, and I'm very, very curious about the whole dark stars thing. Paul, if you have a link to that, please do send it my way, because I want to jump into that and read more about that. So cool. I love finding random new dark matter models to think about. And it's really fun to see all of the ways people are trying to, find dark matter. There are so many possibilities. It's like an infinite playground, so it is fun. That was a great question to get started on, and I just spent 15 minutes on that question. So let me go back to the comments. Scott, sorry to hear you've been in hospital. I hope you're recovering and on the mends. I ended up with a bunch of injuries over the last 2-3 weeks, but I managed to avoid hospital, although I did end up at the emergency doctor, but didn't actually need anything more. So I hope you're doing well. Did you see the Art Technica article about the exoplanet with average density of silver? I did not, but that sounds very cool. Good thing about exoplanets is there are thousands of them. So an exoplanet is any planet that is outside of our solar system. We have found over 3,000 exoplanets by now, 3,000. And this has just been in the last 23 years. Like if you go back to the early 2000s, which was 20 years ago, I'm afraid, if you go back to the early 2000s, we had a handful of exoplanets. We could count them. And now it's like over 3,000. And this is obviously just within the Milky Way, because this is what we have access to. It's quite hard to find planets in other galaxies. It's very hard to find them in our own galaxy as it is. And there are so many different ways we can form planets and that planets can behave. It's like just looking within our solar system, we have a giant planet made of ice. We have Jupiter, which is basically almost a star. Like you increase the mass of Jupiter by 10% and you get a second star. Pretty much, Stargate tried that, not recommended, but it is a thing. And we have rocky planets, we have gassy planets. Just compare Venus that has a toxic atmosphere to Earth. There's just like vastly different playgrounds. So I did not read about an exoplanet that has the average density of silver, but I'm not surprised that such a thing exists. We see it a lot in sci-fi shows that people go off to other planets and they have weird conditions. And it's always very, very cool. Like, there's in Doctor Who, there's a planet made of diamonds with some creepy creatures, or a creepy creature that we never actually see. It's not implausible. So an exoplanet with the average density of silver, I hadn't heard about it. I'm not at all surprised by this. We will find exoplanets across the whole density of possibilities, ranging from gas to big iron giants. It's a lot of possibilities. Given the loose definition of planet, which is basically in orbit around a star, big enough to clear its own orbit, a lot of things fulfill that definition. So there's a lot of things out there that could be planets. And we found a lot of different ones with a lot of different properties. One with the density of silver? Sure, sounds good. Would like to go there, could be fun. What would happen? So silver is more dense than water, because it sinks. So what would happen if a planet is made entirely of silver? I have no idea. Depending on the mass of the planet, you might have cool gravitational effects. Like the gravitational pull on the moon is vastly different to here. That's why people jump. The gravitational pull on Venus will crush you very quickly, and on Jupiter, you get crushed. So it's very cool to think about what different planets would look like, and how would life evolve if it could evolve on such planets? How would life look different to ours? How would it behave? We see a very specific part of the electromagnetic frequency, which happens to align very nicely with what our sun produces. This is not a coincidence. There are animals living deeper underneath the ocean that have a very different visual spectrum to us. Even dogs have a very different visual spectrum to us. So if you were on a planet where the star was blue instead of yellow like ours, or white like ours, what would the civilization, if it evolved, looks like? It's very interesting to think about this. I think we take for granted how much the environmental aspects of our planet, the atmosphere, the sun, the conditions of our planet have influenced the formation of life. So it's very cool to think about. I know I've gone on a complete random tangent here, but it's very cool to think about this. 2010 Odyssey 2 also tried turning Jupiter into a star, not giving any more spoilers. Yes, it's a cool thing to try in sci-fi, right? Let's just take one thing and turn it into a star. Why not? Happy to accept dark matter, dark energy, and all that, but there are adults born after 2000 is just wrong. Yeah, right? There are people in my university like starting master's programs who were born after the year 2000. There are people doing PhDs who were born after the year 2000. It makes no sense. What is time? What is happening? Everything is going too quickly. It is fun. Okay, let me go back to the comments because I know there were some good questions and I keep finding fun tangents to jump on and to go down. Okay, so we saw that our Technica. Whatever happened with the room temperature superconductor? I was expecting people to ask me that. Let me just glance through the comments before I jump into that, because I think that's the next big question. The other ones I've kind of answered as we went along, I believe. Okay, so what happened with the superconductor? That is an excellent question. A couple of weeks ago, it was the big news. So I'm just going to do a very brief recap here. Superconductors are a really cool thing. They allow electrons to move through them very, very quickly, which means they can transport electricity basically unhindered. Every type of thing we use to transport electricity has some type of resistance. A superconductor basically has none. It's really, really, really useful, very fun, has a lot of applications. However, the problem we have with superconductors is they require very, very low temperature and weird pressures. Finding a superconductor that works at room temperature is considered the holy grail of condensed matter physics. It's a thing we're aiming for. It would be a technological revolution if we found one. It would be amazing. It would speed up data processing. It would speed up computers. It would allow advances in medical research and biotechnology. But it's something that is very difficult. So there was a big buzz when a couple months, at some point recently over the summer, a group announced that they had found a superconductor at room temperature and room pressure, ambient temperature superconductor. This was, of course, really, really exciting, really big news. However, it hasn't been reproduced yet. Nobody has been able to independently verify this. And there's a lot of interesting reports coming out now. It seems like it's not completely a superconductor. It might be a diamagnet, which is also fun, which is a slightly different property by which you can kind of avoid electric fields and magnetic fields, but you can have this superconducting effect to the same level. So there are a lot of people looking into it, but nobody has been able to independently verify this claim. And then there was a cool paper, I think a week or so ago, that said actually it's not even a superconductor, it's an insulator, so it just blocks electricity rather than letting it pass completely. It does the opposite effect, but that's weird. I haven't read that paper fully yet, but it's still very murky and very cloudy. And when they advertised it, or when they released the initial paper claiming this, it seemed like it would be very easy to reproduce, but it turns out that's not the case. And one of the problems is that the way it's not just build it in 10 minutes, you actually need to do very specific things to the material in order to try to reproduce this. A lot of people have tried, and it seems like the superconducting claim has not been reproduced yet. So it's gradually becoming less and less likely that it was a room temperature superconductor, unfortunately, because that would have been really cool. But I think it's still very interesting because it's a material that has very cool properties that people are still trying to figure out exactly what these properties are, but it does have very, very cool properties. So that's nice. And it has generated a lot of excitement and a lot of interest in the topic, which is, of course, always nice as well. So I don't think it's a complete failure. It's not what we were hoping for, but it is also very, very interesting, and it's generated a lot of attention. A lot of people have read up about superconductors, have learned about superconductors. A lot of people have suddenly become overnight experts on superconductors, or at least they claim to. So it's very interesting, but it does seem gradually less and less likely that this material is a room temperature superconductor. Some people now are saying even if you reduce it to low temperatures, it's not superconductor. Other people seem to say at low enough temperatures, it is a superconductor. But the idea of a room temperature superconductor might still be a bit far off, but it would be really cool to get it someday. And I think we'll get there at some point, just potentially not now. But still, it is very interesting, and it's been really interesting to follow the developments. I haven't checked in the last week or so what's happening there, but yeah, it doesn't seem like it's going to be a proper superconductor at room temperature. Okay, so Jupiter would actually need like 83 times its current mass to be a star. Yeah, about that. I think that sounds about right. People always say like 10%, but not sure if it's actually 10%, but you don't need to do much to Jupiter to make it into a star. I mean, we can't really make it into a star. But it has the basic constituents. It just needs a bit more density. You could condense Jupiter. Maybe instead of adding mass to it, squash it. Maybe just as a general life rule, don't go out squashing planets, seeing if you can turn them into stars or black holes. But hypothetically, we probably could. Let's see if there's any comments I've missed. I think I'm up to date with all of the comments. So as usual, keep your questions coming. We've had some very fun questions, very fun tangents so far. So do keep them coming, because it's great to talk about these random topics. And if you see me glancing in that general direction, it should be because I've just realized that there's something that is badly placed on my shelf. And now that I've seen it, it's bothering me. But that will be fixed after the stream. That is fine. It's just one of my plants is in the wrong place. So anyway, I mentioned that I'm going to be away for the next couple of weeks. It's actually quite exciting. In a week, I'm heading back to Brussels. So Brussels is the place where I did my first postdoc. I was officially going to live in Brussels for 2 years. And then, the general pandemic happens. Still happening, but we're pretending it's not. But that meant that I was only actually in Brussels for like 5 months. And then I kind of ran back to Germany. But next week, I'm heading back to Brussels, which is going to be very fun. There is a conference called News from the Dark, which is all about dark matter. And I've been to this conference before, and it's really cool because every time I've either participated, I've given a talk in one before. It's really a lot of cool information about dark matter. And I always learn stuff. And when I learn stuff at conferences, it means I have more stuff to tell you all about. So it's a conference that will be about 40 people, all of which work on dark matter and dark matter related things. And there are so many different angles you can take towards, trying to figure out what dark matter is. And the purpose of these conferences is to bring people together with different perspectives. So there's going to be a lot of people working on the particle physics side of actually like building up dark matter models that are reasonable. There's going to be people there working on studying dark matter with galaxies. I was asked to give a talk on constraining dark matter with cosmology, which is kind of broad, and I have 25 minutes, but I'm looking forward to that because I'm trying something new with my slides where I'm reducing the amount of text and increasing the amount of images and making it very clear like what I want people to focus on. I've just kind of revamped my presentation style for this. So it's going to be a fun test. I've been gradually doing this over the last couple of presentations, changing bits and pieces. But I feel like the talk I'm giving next week is very different to the one I gave at the last conference I went to of this series. So it's going to be fun, but it also means that when I eventually get round to doing the next cup of cosmology, whenever that is going to be, I should have a lot more stuff to tell you about dark matter. Probably not going to be we found dark matter. It's more likely to be here's more ways where we looked for dark matter and didn't find anything, but we're still trying. So I'm looking forward to this conference, and I'm looking forward to all of the fun and random things I'm going to learn and can then tell you all about. Assuming I remember, I will take notes. The rule I was always told was a maximum of 5 words per slide. Yeah, Thing is, that's very difficult, right? And it's always hard to find a balance. At some point, I reached a conclusion. So I always try to avoid equations in slides because I think nobody really cares enough about equations to see them on the screen. If you care about the equation, you can read my papers. And then most people don't want to see just a lot of maths on the screen. I personally don't like seeing equations on slides. But I used to have this idea because often in scientific conferences, all of your presentation material is made available for anybody outside of the conference. So it's a good resource, right? So people can go and access your slides without attending the presentation. So with this, I've always tried to make my presentation self-contained so that if you just find the slides online, you can follow without needing to see me talk about it. But that meant text. And I've realized over the years, I've gradually added more and more text. And it's not necessarily the style I want to aim for. So now I've swung in completely the opposite direction. Most slides have a one sentence summary, and that's it in terms of text, but still done in a way where I'm trying to minimize text, but also make my slides self-contained. So it's interesting. Hopefully it will work, but I'm kind of experimenting. And we'll see. And the slides will be available online. So if people want to check them out, I can always link to them. Most of them are actually linked to on my webpage, I think. Did I link to them? I'm not sure if they're linked to on my webpage, but like a lot of the conferences where I've given talks, the slides are available online. And I think it's a very good resource because sometimes you Google random stuff and you come across a presentation that someone gave and then you follow their papers and you learn new things. When I give presentations, I always try to make it how the slides and my words are two different ways to approach the same point. I used to do that, so I like doing that as well. But then there's a problem of like, should people pay attention to the slide or to you? Ideally, both, right? So then you want them to work together, but have different ways of explaining the same thing, but that work in unison. Yeah, I feel like everyone has their own style of presenting, and it's quite difficult to find one that works. I've been told many, many times that I give very good presentations at conferences. So taking what I know works and deciding like, no, I'm going to change it completely is a bit scary. But I did kind of an in-between step at my last conference and the feedback was really positive. So this is going to be the first time where I go like all the way, where every slide is images, one line summary, and it's going to be a fun experiment. So hopefully it will be a good talk, but if not, I can always go back to my old style, which I know works. But it's a fun experiment and it's good to change it up sometimes. Don't speak out your slides, yes. It's also the thing that you don't want to read your slides word for word, but you also want to make sure that everybody in the room is getting the same information, even if they process or access that information differently. So yeah, there's the other thing that if you have a wall of text, nobody's going to pay attention to the wall of text. And what you don't want to do is have a wall of text and read it out word for word, because then nobody in the audience is going to pay attention. But I think everyone has to find their own style. And I have found my style over the years, but now I've decided that I'm changing it. So it's going to be fun. We'll see. We'll see. Depending how it goes and everything, I might just show you my slides in 2, 3, 4 weeks. Whenever I'm next back online, I might just walk through the slides with you as well. Thank you, David, for the comment here. You present really well here. Thank you. I presume in physics seminars you get less interaction. Yeah. So it depends on the conference and where you're presenting. Usually people talk for 15, 20 minutes, however long, and then questions are left until the end. So it's less interactive. But there's always people who will interrupt you if they have questions. And then it very much depends on the conference, like if it's an important question of what does that symbol mean to understand the equation, fine. Otherwise, they should generally be left to the end. So it is very different because here I don't have too much visual material. I have my slide deck, my images ready if I need them. So here it's always more about the interaction with you all. Whereas when I'm presenting at these physics seminars, I have to keep people engaged for the 20 minutes or the 45 minutes that I'm talking without much interaction, and then hope they're still paying attention at the end to ask questions. So the way I approach it is a bit different. The way I prepare for it is quite different. But I think I can obviously, the skills translate, right? And doing Cup of Cosmology, talking to you all every week has really improved the way I give physics seminars. And I think it goes back and forth. But it's definitely a very different style because it's not people asking me stuff and me replying. It's like me info dumping and hoping people pay attention to me. You could present your talk as a stream, yes. So the conference won't be hybrid, unfortunately. There won't be remote participation, which is not ideal. But I can give you a link to the official conference. But maybe next stream I just bring up my slides and we can do a trial and see how that works. I've strung together several bugs and I'm still recovering. And I'm realizing that my voice is breaking now. And we might not go for 1 hour today because I definitely don't want my voice to get worse again. So does the conference typically publish your slides? I know there have been 2 physics questions I've missed. I will come back to them. Does the conference typically publish your slides before or after the presentation? So a lot of conferences use the same platform that is called Indico, which you can host your own Indico server, and then you set up the events. And it's quite a standardized platform, so people are quite familiar with it in the field. And it's also very nice because each speaker can directly upload slides. So I can go into my allocated time slot and upload my slides there. And usually conference organizers ask people to upload their slides the morning of their talk or the day before, like at the latest an hour before the presentation, mainly because if you're in a session where you have 6-7 people presenting, it's a lot easier if the organizers already have the slides, because then you don't need to change laptops or upload and download. There's all that chaos in between. So if you upload them in advance, then whoever's chairing the session downloads them onto the seminar room laptop and then just switches between one and the other seamlessly. I always try to upload mine the evening before my talks because I think it's nice if the audience can see the slides beforehand. I have, on more than one occasion, looked through the slides of a talk to decide if I'm attending it or not. Like if there's 25 talks in a day, you don't go to all of them, you pick and choose. So then if you can see the slides in advance, you get an idea of, oh, this might be really interesting for me, this might not be. Ideally, the abstract will convey that information, but not all conferences have abstracts, and not all abstracts convey the proper information. So it very much depends on the conference and on the chairs, but usually the slides are available at least at the same time as the presentations, unless people are presenting really new confidential results that they have to announce, and then they get to use their own laptops, and then the slides often aren't made available, and then it's a bit, if you have sensitive data, I get why people would do that. But I think it is nice if the audience have the slides in advance, because then it's a lot easier to follow things. What I will do is I will have my slides uploaded in advance and with me on a key stick just in case something goes wrong. You tend to differ on that. If the audience have the slides in advance, I find they read them rather than listen. That is true as well. But, if they read my slides and get the information and then decide they don't need to come to my talk, they've still got the information. I don't really need them to listen to me. If my slides are good enough that they've read the slide and said, yes, I've understood everything, I don't need to go to the talk. Great, I've succeeded in transmitting this information to them. Of course, if they look at my slides and go, oh God, no, I'm not going to this presentation, then I've done something wrong. But I do agree that if people have the slides in advance, there's a risk that they just read them and then don't listen to the person. But also, going back to the example that there was before, people who might have different, who are partially blind, for an example, it might be hard for them to make out what's on the screen. And if they have this in advance and can process it and stare at it on their own laptop, it might help people. So I do think it's nice if people have that, and nobody's forcing people to open the slides in advance and go through them. So I think it's nice if people have that option. So personally, I do try to upload them in advance. And then if people look at my slides and say, I'm not going to that talk, okay, unfortunate. But I can also see why, if you're going in there with the idea, like, I want the audience to focus on what I'm saying and not so much on the slides, then sharing the slides in advance might not be as useful. Some people always prefer to use their own laptops if they're showing videos or animations, and then they might not necessarily upload their slides. before the talk, and then maybe they upload a version after the talk where they've removed the key plot or something. So it very much depends on the person, on the conference, but in general, the slides are made available, and it is, I find, a very useful resource. Of course, it's annoying when you find somebody's slides from like 3 years ago and you're trying to figure out what they meant, and you're just staring at a figure on a slide that never appeared in a paper, and you're like, But yes, there's a lot that goes into it, and I get that not everybody wants to make their slides available in advance. Okay, there were 2 physics questions. Going back to one of them there, where was it? Oh, we saw that one. What's the logic behind smaller a black hole, the faster it emits Hawking radiation? Intuitively, it makes more sense for larger black holes to emit more Hawking radiation. Excellent question, complicated question. So I think when we're talking about Hawking radiation, what matters is not so much the mass, but the surface of the black hole. Now, of course, a bigger black hole has more surface through which you can have Hawking radiation. Now, again, Hawking radiation is not stuff escaping from a black hole. It's particles being pair produced on the event horizon. One falls in, one goes out. The one that goes out carries away mass from the black hole to compensate for just being created from nothing, essentially. So the larger the surface area, the more places where Hawking evaporation can happen. However, as a black hole gets smaller and smaller, if you imagine, so we have the idea with black holes that this is known as the holographic principle, that all of the information of a black hole is contained on its surface, which means as it gets smaller and smaller, there is less surface available for it to contain that information. So that information has to escape faster and faster, if that makes sense. But it's something that mathematically you can derive, but it's basically comes down to, as the black hole gets smaller and smaller, the overall surface involved is getting smaller and smaller, so the information that is on the surface has to go away quicker and quicker. So the evaporation is going to be slow as it's bigger and speed up as it gets slower, as it gets smaller and smaller. Now, this is very hypothetical. We have not ever seen Hawking radiation happen. We don't know if it does happen. We think it does, but yes, it's still hypothetical, but it is a very cool phenomena. And this whole idea of the information being contained on the surface of a black hole is also something that is very theoretical and very difficult to actually test in any meaningful way. There's a lot of people working on this, but it's something that makes a lot of sense mathematically, but is very complicated to explain, at least for me personally. Voice is definitely not happy about me talking so long, which does not bode well for giving 3 talks in the next 4 weeks. Anyway, I should be recovered by then, no problem. Yeah, so Hawking evaporation, this idea that particles are pair produced on the event horizon, one goes out, one goes in, is something we haven't observed yet, but it's something that is deeply mathematical. And it's a problem that of what happens when we try to combine the gravitational world that is our black holes with the quantum world that is like pair production of particles. It's very difficult to put these 2 together. But as a black hole gets smaller, less surface which can participate in the Hawking evaporation, so the process speeds up, if that makes sense. It's kind of hand-wavy answer to that question there. I would actually have to look into it properly and play about with the equations to be able to give a more detailed answer than that. But it is a great question, and I'm glad you asked that, because it's always fun. And it makes me think again that, I should do a stream about Hawking radiation. I feel like I've done bits of streams about Hawking radiation, but not one in depth. Maybe I can get the dynamic duo back for part 2 of Quirks and Creativity with General Relativity. Get my dynamic duo back on, and we could talk about Hawking radiation in a bit more detail. That would be fun. I'm absolutely outsourcing this question to other people, so I'm going to try to get other people come on my stream to answer that question. Also, I know you all like the dynamic duo, and they haven't been on in a while, so I'll see if I can get Ali and Lorenzo back on the stream together. There was another question that I'm pretty sure was just to provoke me and for me to give a long answer, but I'm going to answer it anyway. What is your opinion on MOND? So MOND is modified Newtonian dynamics. It's the idea that we don't need dark matter to explain things in the universe. It's just our understanding of dark matter. So our understanding of gravity is wrong. So the key idea of MOND is we have a universe that does not have dark matter, and instead we're just missing a piece of the puzzle in terms of gravity. So MOND is a subtype of modified gravity. Modified gravity is the idea that you modify all of gravity to explain things like dark energy or dark matter. MOND is a subset that focuses on some specific observations and some specific modifications to gravity, focusing on Newtonian dynamics. That's where the name comes from. Now, I have one issue with MOND. MOND is very, very, very good at explaining the rotation curves of galaxies and a few local observations that we've also used to explain dark matter. So the way matter moves around in galaxies doesn't go completely as we expect. And the way we've been able to explain this is with dark matter. MOND can also explain the motion of stars in galaxies. However, the dark matter is not just about galaxy curves. There's also the way galaxies look when they smash together, such as with the bullet cluster. There is the distortion of light as it passes through massive objects, gravitational lensing. And of course, there is my all-time favorite, the CMB, the cosmic microwave background radiation. This is a snapshot of what the universe looked like 380,000 years after the end of inflation. This shows us the statistical properties of the baby universe. Explaining this map without dark matter is extremely difficult, and we have not been able to explain why the CMB looks this way without using dark matter. So my biggest problem with MOND is that it cannot explain the CMB. Of course, you could argue maybe it's not its job. Maybe you use MOND to explain galaxy dynamics and something else to explain CMB and weak lensing. But why take two or three things when dark matter does these things for you? So it's I think it's very good that people are working on MOND, and it's good to test our assumptions and to go back to basics and ask, what are we missing? Is there something we've done wrong? So yeah, it's something that is very useful to work on. I just find it quite hard to like a model that ignores the CMB. Of course, the universe doesn't care whether I like a model or not, right? It doesn't care about our own individual opinions. There was a conference when I was in Aachen in Germany. So in Germany, in the group in Aachen, there's a subset of people working on philosophy of physics, which is a really interesting topic. And they had the idea to bring together people working on dark matter and people working on MOND, kind of a 3-day conference. And a lot of people came to this conference with different ideas. And there were some talks that were like, here's why dark matter works, here's why MOND works. And almost all the MOND talks started with, so let's ignore the CMB. I'm like, well, come on. If you start like that, how am I going to pay attention? So I think MOND is a very interesting framework, and I'm glad people are investigating it and trying to see if there's something we've missed, because maybe dark matter is not the answer. But if you have a model that can explain 6 or 7 different observations across different scales, and one that can only explain 1 or 2 of them, then it makes more sense to lean towards the one that explains more. But that doesn't necessarily mean it's the correct answer. So this is me being very diplomatic today and not ranting. So I think MOND is very, very interesting model, and I'm glad people work on it. It's one that personally I don't think is the best fit to all of the data that we have available. So I lean much more towards dark matter than MOND, but it's good that people work on MOND as well. Today was a twofer. You got one of the earliest CMB appearances and one of the most frequent CMB reappearances. Yeah, we've had it 4 times today, maybe 5. I've lost count by now. It keeps appearing. I mean, how could it not appear? It's just such a pretty image. There are 3 CMBs up in my office around me. So, you can never, ever have too many CMBs appearing. If I leave a microwave on with the food open, will it become part of the CMB in 14 billion years? Hypothetically, yes. However, every microwave has an automatic kill switch. As soon as you open the door, the microwaves stop emitting waves. There used to be this thing that went around like, never open a microwave while the time is still on or you'll get hit by microwave radiation. And this always seems so weird to me because, one, microwave radiation is pretty harmless. We're constantly bombarded by microwave radiation from the CMB. It's kind of harmless. And two, every microwave, by the way it works, cuts out as soon as the door is open. If you don't have a closed circuit, you do not create waves. So if you leave a microwave on with the food open, okay, I've realized that's not actually what you said. I read the door open, not the food open. So if you leave a microwave on indefinitely, producing waves that will eventually be part of the CMB in 14 billion years. But by then, the CMB will have shifted so much that it will no longer be in the microwave range of the electromagnetic spectrum. Here's the cool thing. We are alive at a time where we can see the CMB, where we have access to this map. And this is not a given. If we'd been alive a couple billion years ago, this would have been very, very bright. A couple of years previously, it would have been in a different range. And in the future, it might be in a completely different range and not visible. There might be a generation or a civilization a few billions of years into the future that will not see the CMB because it will be so redshifted that it will not be visible, which is not good to think about. I'm superstitious. I wait until it does 3 beeps after finishing before opening the door. That is valid. I try to open it with 1 second remaining because then my microwave requires like 5 buttons to get it going because it's a micro oven combo. And if you stop it when there's a few seconds left, then you can just put it in and add the time on. You don't need to reset stuff. So I always try to open it before the timer runs out, but everyone has their own thing. Didn't military warn themselves in front of radar waveguides in cold climates? Probably. Yeah, I think people hear the word radiation and think, oh, radiation must be bad. Not all radiation is bad. X-ray radiation, gamma ray radiation, probably don't stand in front of it. But yeah, in general, radiation just means like particles of light, photons. Everything we see is radiation. So radiation by itself is not a bad word. It's what you do with radiation. If you make gamma ray radiation or X-ray radiation, that could be more problematic. Radiation by itself is not a problem. It's fun. But yes, in general, don't stand in front of random gamma ray sources if you can avoid it. Still don't understand how black holes lose mass through Hawking radiation. If a proton is emitted, then shouldn't the antiprotons falling in increase its mass? So you pair produce 2 particles on the event horizon. This is something that you can do often. It happens continuously in the universe. The universe kind of borrows energy from itself, produces these 2 particles, they then annihilate and return the energy. Producing these 2 particles requires energy. This energy has to come from somewhere. Usually it comes from the vacuum energy of the universe, fancy jargon. So you kind of borrow energy from the universe, you produce your 2 particles, and then they annihilate and return the energy. But if you pair produce the particles, you've borrowed energy, and then one falls into a black hole and the other goes away, they can't annihilate. So they've kind of stolen energy from somewhere. Energy must be conserved. So the way this is maintained is the particle that is escaping kind of steals the mass of the black hole because then it's adding energy to the overall universe to pay back for the energy that was used to pair produce the particles. But it is weird, and it does make sense. If you think about particle falls into black hole gets bigger, yes. But here it's falling in a way that is kind of the more important process is the one that's escaping. And that's the one that is carrying away energy, carrying away mass from the black hole because it borrowed this to create the particle in the first place. But it is a weird, very confusing topic. So I know I'm giving hand-wavy explanations that might not be completely satisfactory, and I'm sorry for that. I will try to do a proper Hawking radiation episode at some point because it's a really fun topic. White and black time has run up. The universe is coming to destroy you all. You can't survive the sun like the chocolate skin. I'm not sure what you're talking about there. The universe is not coming to destroy us. The universe doesn't care about our existence. We will probably be killed at some point by a lot of random things, but the universe is not out to get us. And hopefully we will at some point survive. But that was an odd comment. Okay, military warming themselves in radar, we saw that one. Okay, so what if you hacked a microwave that doesn't need to have the door closed? Well, okay, so you hack a microwave and then you leave it on emitting constant microwave radiation. That will eventually go somewhere. Yes, it's probably not going to be harmful, and it might eventually be part of the CMB for a distant planet if they can still see it. What's likely to happen is it's going to be redshifted so much that it's not going to be something that we need to. It's going to be redshifted so much that it wouldn't be visible by the time it would be part of the CMB, if that makes sense. So yes, if you have a microwave, you leave the door open. You've hacked it so that it works with the door open. You're producing microwaves. These are just going to go there. Eventually, they will be some type of radiation. Well, they are radiation. Eventually, they might join some other type of radiation, but they probably wouldn't make it out to the CMB because there's going to be a lot of stuff that's going to block it. Like, first of all, they need to escape your house, and there's walls in the way, and walls tend to block a lot of lights. And then they have our atmosphere to get through where they might interact with other particles. So there's a lot that can happen to the photons that are produced in your microwave, or the electrons that are moved around in your microwave. There's a lot that can happen to those once they leave your microwave, assuming you've hacked your microwave so they can actually leave. It's a cool thing to think about. Where do trains go to sleep? I'm sure that's a question everyone's wondered at some point. I love seeing where trains go to sleep, like seeing a train station at night with all the trains parked there was amazing. Anyway, the question of where do microwaves go when they escape a microwave oven is a very interesting one, and it feels like a deeper question than it actually is, but it's a fun question. Okay, I said I wasn't going to go for an hour, and we're 57 minutes in, so of course we did almost go for an hour, as fully expected. I think I got through all of the questions and all of the comments today. If not, as always, do feel free to ask it again, because maybe I missed a comment, maybe I missed a question. There's a lot of comments and it's always hard to keep up. So if I miss something, do feel free to ask it again. We'll try to answer. If you want to ask me something or send me something outside of Cup of Cosmology, the easiest place to find me now is on Mastodon. I have a Mastodon account that is specifically for cosmology outreach. So if you follow me on Twitter, I am not using Twitter anymore because I have a lot of issues with the person who runs Twitter and the way Twitter is being managed and literally everything happening on Twitter these days. So Twitter is only used as one of the channels that this stream goes to, but I will not be interacting with people on Twitter much. So the best place to follow me these days is on Mastodon. I have two Mastodon accounts, one which is my more personal ramblings where I post random stuff, including like, hey, look, I made a cake. And one that is purely for science outreach. Sometimes they cross over. But the science outreach one is dchooper91_cosmo on the server astrodon.social. There is a link to this pinned on my Twitter profile, and it is also available from the Cup of Cosmology webpage. So feel free to follow me there, interact with me there. If anyone needs help setting up a Mastodon account, let me know, and I will be happy to help you out there because I think everyone should be on Mastodon. So feel free to reach out to me on Mastodon. You can try me on Twitter. I might see it eventually, but if I don't reply to you on Twitter, don't take it personally. I'm not replying to anybody these days. Not on Twitter. And as always, if you go to the Cup of Cosmology webpage, there is a button to contact me and send me an email through the official Cup of Cosmology email address if you want to as well. Although I don't tend to answer science questions there because it would take up too much of my time. So thank you everyone for joining. It's been great fun. We've had some fun questions, some fun tangents. As I said before, next week there will be no Cup of Cosmology. I will be on a train on Sunday next week, I believe. The week after there will be no Cup of Cosmology. I will be in Barcelona, I believe, and it's hard to keep track. And then on the 24th, I travel back. I might be completely exhausted and not in the mood for Cup of Cosmology. I'll decide on the day, so that one will be a bit last minute, but we'll see. I get home like 3 hours before the stream is due to start, so we'll see if that's actually happening. But in any case, in October, we'll be back to regular schedule. I'm not planning any more traveling after my next few chaotic weeks, so things should calm down and stabilize a bit after that, hopefully. So thank you everyone for joining. This has been really, really fun as always. It's been great to have you all here. Had some really cool questions, always fun. I'm going to go rest my voice a bit now. So thank you everyone for being here. I hope to see you all again at some point in the future whenever Cup of Cosmology is back on, probably 3 weeks from now. I hope in the meantime you'll stay safe and take care of each other.